In this video, we discuss the barrier problem and its application in tiled matrix multiplication using CUDA. The barrier problem is a synchronization problem involving n threads or processes. In this scenario, threads reach a barrier but cannot proceed further until all threads have arrived at the same point. This synchronization is especially crucial in applications divided into phases, where no thread is allowed to advance to the next phase until all threads have completed the current one. Once threads exit the barrier, it resets itself, allowing threads to end again for subsequent synchronization. For your reference, we present a solution to the barrier problem, but we won't delve into its detailed discussion here. CUDA simplifies this process by providing the command sync threads, which synchronizes threads as they reach a barrier. We discussed matrix multiplication in a previous video. This diagram shows matrix A times matrix B to give us matrix C. The dot product of a row vector of A and a column vector of B will give a corresponding element of C, and by this formula. So if A is m by n and B is n by L, then C is m by L. And in a previous video, we discussed the fundamentals of matrix multiplication using CUDA multi-threads. So in CUDA, a block contains one or more threads, and a grid contains one or more blocks, as shown in this diagram, which we discussed last time also. So this is a grid that contains a group of blocks, block 00, block 01, block 02, block 03. So the x dimension of this grid is 4. The y dimension of this grid is 3. And so this is block 00, block 01. And for example, this block 1, 2. So the x value of this block is 2, and y value of this is 1, or in I is 1, j is 2. So for this block, it consists of many threads. Say we have in a row 5 threads, so the x dimension is 5, and in the y dimension it is 4, and z is 3. So that means thread idx.x is 1, thread idx.y is 2. For this thread. Now, this is the code that we discussed last time, how to use the multi-threads to do matrix multiplication in CUDA. So in the example, m is 64, n is 62, l is 64, m and l here. And the maximum number of blocks that is allowed in a block is 1024. And define the constant square root 2 here. So in the matrix multiplication, we use ij to indexing an element of C, okay, and ij, an ij element C is handled by one thread, okay, in a particular block, okay. So so ij can be calculated in this way, okay. So basically, each thread gives a pair of ij, and each ij pair is indexing the element Cij, okay. So today there are m times l threads work in parallel, okay, and each thread calculates a sum, okay, using this formula, okay, or here, okay, and all these are working in parallel, okay? And so each thread calculates the sum, okay, the dot product between a column and a row, and we save the element, okay, in the C matrix, okay, C matrix, C array. Okay. So here we divide the threads per block, okay, and blocks per grid, okay. So that's what we discussed last time. So now let's copy this and try again. We copy this. Okay. So, and we save it in matrix mo.cu. And paste it. Okay. So this is our CUDA program. And now let's compile it. So we say mvcc, okay, made mo cu minus o. And so it's compiled, and we can execute it. Okay. So the passed, okay, and so this error check just checked all the elements to make sure that each element is 2 times n, because square root 2 times square root 2 is 2. Okay, so the dot product of a row vector of A and a column vector of B will be equal to 2 times n. Okay, we just check all the elements and print out just the first one. Okay. And we can check the profile, okay, using MV Pro. And you can see that the kernel core, okay, takes about 54.5 microseconds. Okay. Now, this matrix multiplication may be accelerated using a method called tiled matrix multiplication. The diagram here shows the memory structure of a GPU. Okay, so this is a grid. Okay, The grid consists of the different blocks. As you can see in this diagram, you have different kinds of memories: shared memory, registers, global memory, constant memory. Constant memory is some read-only memory that's fast. Okay. And global memory is the main memory. Okay. The data are stored in this main memory. Okay. And registers, of course, is register in the GPU. And now, shared memory, okay, is some fast memory within a block. Okay. So its amount could be small, okay, but it's much faster than the global memory. It could be sometimes 10 times, 100 times faster. Okay. So within each block, there's a shared memory. And this shared memory within that block could be accessed by the threads in that block. Like block 00, we have thread 00, thread 10. Okay. And another block has another shared memory. Okay. And this shared memory is independent of the memory in the other block. Okay. So in this example, okay, the example here, so the data are divided into tiles or blocks. Okay, so each block or each tile of the data correspond to a block in the grid. Okay, and we will load the data of a tile into the shared memory so that it could be retrieved and read very fast. Okay, and then we perform the operations. Okay. Now the crucial thing is that the different thread blocks have their own separate shared memory. So this shared memory is independent from this shared memory. So in this way, multiple blocks execute the same kernel code concurrently without interfering with each other's shared memory usage. Okay. So this block works independently from this block. Okay. And of course, the threads within a block access the same shared memory. Okay. So let's see how we can make use this to do tiled matrix multiplication. Now here's an example of dividing the matrix A and matrix B into blocks of data. Okay, in this example, each block is 4 by 4, or each tile is 4 by 4. Okay, and the same for C. Okay, so in this example, the tile size T is 4, and the grid dimension, basically the matrix size. Okay, in here C is equal to A times B. Okay, is M times L. Okay, A is M times N, B is N times L. So C is M by L. Okay, and the grid dimension, that means the number of blocks in a row, okay, is L divided by T, the tile size, and the number of blocks in a column is M, okay, divided by T. Okay, here it is 4, okay, and then 4 here. Okay. Now here's the code to implement the tiled matrix multiplication. Okay. So we pass in the variable n tiles. There's the number of tiles that we have. Okay. And we declared arrays in the shared memory. Okay. We declared 2 arrays, okay, using this syntax, share and double. Okay. SA 2-dimensional tile width here, tile width is 4, okay, and SB. Okay, so we declared SASB in this shared memory for this block, and then other SASB in this block, and so on. Okay, so tile width, for example, in the example here, it is 4. Okay. And so ij will be indexing a C element or corresponding to a thread. Okay, this calculated in this way. Okay, like I is index y, okay, plus the block y times tile width. Okay, so this is the row, this is the column. Okay. The tile width is basically the block size. Okay. So for example here, okay, this element, green, okay, the ij is 6, 6. Okay. So this in the, block 1, 1. Okay. And we define the variables local I, local j to be the index given by the thread, okay, yx. Okay. So that means within this block, okay, so this is the element 0, 0, 1, 0, okay, 2, 0, okay, the same for this, okay, within this block, okay, within this tile. Okay. So we perform the calculation of the product between 2 submatrices. Okay. So that's what we do here. Okay. So we divide the sum. Okay. It will be 0 at the beginning. We have to loop through the tiles. Okay. There are that many tiles. So we start from t equals 0. That means this one. T equals 0 is this tile. This tile. So we find the product of these 2 submatrices, and then we advance t to be here, okay, and so this will multiply this to give us another submatrix, okay, and now here's t equals 2 in this example. T equals 2, okay, this is t equals 2, the tile, so within this operation, so this row, okay, will multiply this column, so give us this element, okay, for this particular 2 blocks, okay, to give us one particular value, okay, and eventually we need to sum up, okay, all these values from the product of each 2 blocks. Okay, so that's why we need to do a loop through all the tiles, okay, n tiles. In this case, is 4. Okay. And also for each tile, we load the memory from the global memory into the shared memory, like the SA. Okay, so we load the memory, okay, into the shared memory. So when t equals 0, okay, we load this this guy here, okay, and then when t equals 1, we load this guy. Okay, the same thing for B. When t, okay, equals 0, okay, we operate on this block. This block is loaded into SB. Okay, so using these formulas. Okay. So SA, the A elements are loaded into SA. So this is basically a block or a tile. Okay, and of course we load the value only when ij is within the boundaries of our matrix. Okay. Otherwise we set the values to be 0. Okay. And now we wait until all threads within the block or the tile have executed this same threads. So, but we do not need to wait for another block, right? Because blocks operate independently on the shared memory. Okay? But within the block, we'll wait for it. Okay? And then a thread in the block, we perform the sum. Okay, basically using this formula. Okay, perform the sum. And now when we go through the tiles, okay, we have to add all the sum together, because we define the sum outside this loop. Okay, so if block will give us a sum, and then we wait for all blocks to finish before all threads to finish before we advance. Okay, and so that means eventually your sum, so like the sum here, will add the top product for between this guy and this guy and this guy, this guy, and this guy, this guy. Okay, so we get the final sum, and then we put this sum in the C matrix. Okay, the final sum. Okay. So that's the piece of code. And for the main, we just need to define the threads per block to be the tile width. Okay, now in this example, 4 times 4. Okay. And then the blocks per grid would be equal to L divided by tile width and M divided by tile width. Okay, we need to do the cast of float because this will be an integer division. It will truncate the value. Okay, unless we cast that to a float. Okay. And the number of tiles will be equal to n divided by tile width. Okay. The number of tiles in one row, okay, of A or one column of B. Okay, so that would be equal to n divided by tile width. Okay, and then we call the kernel function, okay, using the blocks per grid and threads per block that we calculated here. Okay, so this is the modification we have. Now let's try this. First, we copy the made CU, the one that we have, to maybe tiled made the CU, okay, and then make some modification. Okay. So this will be our tiled memo. And so we don't need to change all this. We don't need the maximum block here, but we define the tile width here. Tile width, maybe we use 16. Okay, 4 is too small. And this is the kernel function that we need to use. So copy this. So we'll paste this one. Okay, so that's our new function. So we don't need this one anymore. Okay, and then we do some modifications on the main. So we just need this part. And we don't use this. And here we need to calculate the n tiles. The number of tiles in the row of A or column of B. Okay. And here we add this parameter n tiles. Okay, so others are the same. N tiles, okay. So this is it. Okay, and now let's compile this. NVCC tile. Okay. And now we can execute this. So again, a pass, we get the same result. And you can check this with the profile. Maybe use this terminal. So it has some improvement, okay, as compared to the other one. This is 33 microsecond as compared to the other one, which is 54. Okay, so the because of using the shared memory, okay, we make some gain in speed. Okay. Now. Let's have another example of using the tiled memory to do operations, okay, that could speed up the process. Okay. Let's consider the example of the tiled, calculating tiled dot product of two vectors. Okay. Now this is the standard code for calculating the dot product. Okay. Again, it's very simple. The dot product of two vectors. Okay. So we have two vectors with each with size n equals 10,000. Okay. Again, we define square root 2 to be 1.412. Blah, blah. Okay. And the dot product, okay, of A and B, okay, would be basically a sum of the product of the elements of A and B. Okay, very simple. And then we just put the sum into array C. Okay, C0. Okay, and check array here. We just need to check one element. Okay. And so again, we set all AI to be square root 2, be the same for square root 2. So the dot product will be, say, 20,000. Okay. So again, this standard. And so suppose we use one thread to do it. Okay. And see how this works. So this is dot product. Okay, and let's copy this. Okay, so this dot product.cu. Dot product.cu. So copy this. Save it and compile it. Product. So we got the value we expected. Okay, and you can check the profile. Okay. So it takes about 1.2 milliseconds to do all that, all the calculations. Okay. Now, if we use the tiled method we discussed, okay, then it could be significantly faster. Okay, so still these are similar. Okay, so we define a shared memory. Okay, tile width here is 1024. Okay, and so this is the shared memory. Okay, and so we divide, say, the vectors into tiles. Okay. And each element is accessed by a thread ID, which is given by this thread idx.x plus block idx.x times block dim.x, okay, the thread ID. So this one dimension only. And again, before we define the local TID, local thread ID, okay, that's within the block. Okay, so the thread idx.x. Okay, and now each thread will calculate its own sum of products. Okay, we divide the vector into different tiles. Okay, and we look through the tiles. Okay, in this case. We do the sum, okay, to be the sum of a times b, ak times bk, okay, and we jump over from one element, okay, to from one element in a block, okay, to another element, okay, in another block. Okay, so that's our sum. Okay, and then we put this sum, okay, into the shared memory, okay, or the tile shared memory with local TID. Okay, so that's the sum, and then we again wait for all the threads to finish, and now we do a reduction within the block. Okay, and we can do that in parallel. So we have the data within this block. Okay, so this we have a thread adding this element with this element. So this stride, we start with block dim the x over 2. Okay, so this and this. And this thread, another thread will do the addition of this and this, and put that into this array location. Okay, and the thread and the third will do this or this and this. So eventually we get this. So after one round, we reduce the value by 1/2. I mean the rate that we need. Okay, and then we continue this process. So the next round, this thread will add this and this. Okay, so so we continue this as long as stride is larger than 0. Okay, we have in each iteration we do this. We'll do this sum. Okay, and then at the end, we just put this value. Okay, eventually, the value will be saved in tau 0. Okay, we put that into a location of C indexed by the block. Okay, we have n blocks. Okay, or n tiles. Okay. So here's the main. Okay, so we define n blocks to be the Sinning function between n divided by tau width. Okay, a number of blocks. Okay, and then C will be n blocks. Okay, and again we use n blocks, and each block has that many tau width threads to do the operation. Okay. And after that, the values of different blocks are saved in C. So we have to do the final step to calculate the final sum. Okay, and so this is that with us n blocks. So n blocks could be say just say 10 here. Okay, but the tau width is large. Could be 10, 24. Okay, now so let's try this program. And again, let's first copy this dot product.cu to tau dot product.cu. Okay. Oh, sorry. It's a typo. Okay, so this is a tau dot product. Okay, and here's the code. So all these are not changed. And we don't need this anymore. Okay. And in the main, so we need a larger C array. This should be here. Okay, so we have all this, and kernel function calls would be like this. So delete this. And then finally, after that, we need to sum up the partial sums. Okay, so that's our program. That is let's compile this. MVCCA tilde dot product. Okay, so execute. So we again get the correct result. Now let's compare this with the previous one. Profile. Now you can see that the kernel call just requires 12.2 microseconds, and before it takes 1.2 milliseconds, so it is significantly improved, okay, by using this tilde method. Oh, do it again. Yeah, 12 microsecond, okay, versus 1.2 millisecond is yeah, much faster here. Okay. So that's what we are discussing today. Okay. So if you feel that the video is useful to you, okay, please give it a like. Thank you. I'll see you in the next video. Okay, bye.